Hey you guys, this is Mr. Millings, and today I just want to go through a few gas law problems and show you guys step by step how to do these problems. Some of these problems might appear on a test or a quiz that you might take in your chemistry class. So let's take a look and work some problems out. In this first problem here, it says a balloon has a volume of 5.3 liters at 49.7 degrees Celsius. The balloon is then heated to a temperature of 78.1 degrees Celsius. The volume of the balloon after heating will be blank liters. Alright, so in this problem here, if you take a look, we've got a problem here that is dealing with both, let's see here, volume and temperature. So you have to ask yourself, what formula do I know uses both volume and temperature? Well, that is going to be a Charles law problem, right? We've got volume here because it's liters, and we've got temperature here because it's degrees Celsius, and no other variables happening here. So this is going to be a Charles law problem. So we know that V1 over T1 is going to equal V2 over T2. And if you want to get rid of these fractions, what we can do is cross multiply. If we cross multiply, we will end up with the formula V1 times T2 equaling V2 times T1. And when we work with this formula, before we can start plugging numbers in, we have to make sure that the temperature units are in Kelvin. These are in degrees Celsius right now, but whenever we work with gas law formulas or problems, we have to make sure that the Celsius temperature is in Kelvin. Alright, so let's do that. Let's see here. This is, well, let's read through this first. It says a balloon has a volume of 5.3 liters, so this right here is going to be V1. At this temperature, this right here will be T1. The balloon is heated to a temperature of this right here. This looks like it's going to be T2. And we are asked to find the volume. We want to know the volume of this balloon after it's heated up. So we're trying to find V2. Okay, so the first thing I need to do is convert T1 to Kelvin. So we have 49.7 degrees Celsius. And the way that we convert Celsius to Kelvin is by adding 273 to this. Get your calculator out. 49.7 plus 273 equals 322.7 K. Let's find out what T2 is going to be. T2 is 78.1 degrees Celsius plus 273. Put this in our calculator, and we get 351.1 K. So now that we have these temperature units converted from Celsius to Kelvin, it looks like we can go ahead and plug these numbers into our formula here. So in this formula, it looks like we're asked to find V2. We want to solve for V2 here. So how do you get V2 all by itself on one side of that equal sign? We're going to divide both sides by T1. If we divide both sides by T1, it looks like the formula that we will use to solve this will be V2 equaling V1 T2 all divided by T1. So now we can just plug these values in. In this problem, it says V1 is 5.3 liters times T2, which it says right here is 351.1 K. 351.1 K. Let me erase this right here. And we're going to go ahead and divide this by T1, which is going to be 322.7 K. So we'll get our calculator out and take 5.3 times 351.1 divided by 322.7, and we'll get our answer. And we're going to go ahead and round all these to the thousands place. We're not going to use significant figures here. If your teacher is requiring you to use sig figs, please pay attention to the sig fig rules. But we're just going to round this to the thousands place. Our final answer here is 5.766. 5.766 what? Well, Kelvin will cancel out, leaving you with liters. Alright, and what I like to do right afterwards is just figure out once I have the answer, if it's making sense. If you take a look here, the temperature is increasing. It's starting off at 322 going to 351.1. So the temperature is increasing slightly. So according to Charles' law, if the temperature is increasing slightly, then it looks like the volume should also be increasing slightly, and in fact it does. It's starting off at 5.3 liters and it's going up to 5.766 liters. Let's look at this next one here. In this problem here, it says an aerosol can is at a pressure of this right here. So this is going to be P1. This is going to be your starting pressure. At a temperature of this right here will be your starting temperature. It is then placed in a fire and the pressure is increasing to this. So the pressure has increased to this, and we want to know what T2 is going to be. So we are asked to find what the new temperature will be. So in this problem here, how do you know what formula to use? Well, we're dealing with pressure and temperature here, and that is going to be a Gay-Lussac's law. Alright, Gay-Lussac's law states that P1 over T1 should equal P2 over T2. And once again, we can cross multiply to get rid of these fractions here. And if we cross multiply, we will end up with P1 T2 equaling P2 T1. And once again, before we can just start plugging the numbers in, what we have to do is we have to convert the temperature units to Kelvin. They're in degrees Celsius right now. So T1, it says right here, is equal to 20.1 degrees Celsius. I add 273 to that to convert it to Kelvin, and it looks like this is going to equal 293.1 Kelvin. And I need to do the same thing with T2. With T2, oh, never mind. Looks like that's what we're trying to find. We're trying to solve for T2. I apologize. So now we've got our temperature unit in Kelvin, and we need to make sure that the pressure units are the same. We've got atmospheres here, and we've got atmospheres here. They appear to be the same. So now we can go ahead and work with this formula. And in this formula, we're trying to solve for T2. So to get T2 all by itself on one side of the equal sign, what we will do is we'll divide both sides by P1. These will cancel out here, and so T2 is going to equal P2 times T1 all over P1. We just put our variables in now. P2, it looks like it's going to be 29.6 atmospheres times T1, which we just figured out was 293.1 K. And we're going to divide this all by P1, which is 1.3 atmospheres. Getting a little crooked here. I'll try to straighten out for the next problem. And we end up with 29.6 times 293.1 divided by 1.3, and we end up with 6,073.661. I'm sorry, 6,673.661 atmospheres will cancel out, leaving us with Kelvin. So there is our new temperature of this gas after this aerosol can is thrown into the fire, apparently. And does the answer make sense? Let's think about this. The pressure is increasing. If you take a look, the pressure is increasing by about 25 times. It's going from 1.3 to this. So it looks like our temperature here should increase by about 25 times. And if you take 25 times this, you'll end up with something fairly close to this answer right here. So that's one way of just kind of quickly checking to make sure your answer is correct. Let's take a look at the next example. In this example, it says at constant temperature and pressure, 1.7 moles of gas occupies 6.2 liters. What will its new volume be if the number of moles decreases to 5.9 moles? So in this problem here, we are dealing with moles and we are dealing with liters. Moles and liters. So what formula do we know uses moles and liters, or volume? That is going to be an Avogadro's law problem. And in Avogadro's law, we know that V1 over N1 equals V2 over N2. And if we cross multiply and get rid of these fractions, we'll see that V1 times N2 will be equal to V2 times N1. And in this problem, it looks like we want to know its new volume. So we're asked to solve for V2. So if we're asked to find V2, we divide both sides by N1 here. And our formula that we're going to use to solve this problem will be V2 equals V1N2 all divided by N1. So we can just go ahead and plug these values in. At constant temperature and pressure, it looks like the starting number of moles of gas is right here, and the starting volume of this gas is right here. So there's N1 right here, here is V1 right here, and we want to find V2. Looks like this is going to be the moles of gas is increasing to this, so this is going to be N2. And so now we can just plug these in. It looks like V1 is 6.2 liters. We're going to multiply this by N2, which is 5.9 moles. And then we're going to divide this by N1. Looks like N1 is going to be 1.7 moles. We'll put this in our calculator. And we got 6.2 times 5.9, and we're going to divide that by 1.7, and we end up with 21.518. Moles will cancel out, leaving you with liters. So the final volume of this gas is going to be 21.518 liters. Does this answer make sense? Well, if we take a look here, we know that volume and number of moles in Avogadro's law are directly proportional. So if we take a look here, the number of moles is increasing from 1.7 to 5.9, somewhere about 3.5 times. So our final answer should be about 3.5 times this, and in fact, if you take 3.5 times 6.2, you'll end up with something pretty close to this answer right here. So that's how we know we've done it correctly. Let's take a look at another problem. In this problem here, we have 577 milliliters of gas at this temperature right here. So it looks like this is going to be the starting volume, and this right here is going to be the starting temperature. It is compressed to this right here. So this is being compressed to this right here. So it looks like this is going to be V2. And the new temperature of the gas is what we're asked to find will be what? We want to know the new temperature of the gas if the volume is decreasing from 577 milliliters to this right here. So in this problem, we're dealing with volume and temperature, and therefore this is going to be a Charles law problem, which states that V1 over T1 equals V2 over T2. Once again, we'll cross multiply to get rid of these fractions, and so V1 times T2 is going to equal V2 times T1, and in this problem we're asked to solve for T2. To get T2 all by itself on one side of the equal sign, we'll divide both sides by V1, and so the formula that we're going to use to solve this problem is V2 times T1 all over V1. Before we can start plugging numbers in, we have to make sure that these volume units are the same and that the temperature units are in Kelvin. So let's take a look here. We have milliliters here for volume, and we have milliliters here for volume, so we're good. But take a look. T1 is 46.2 degrees Celsius. So I need to convert this to Kelvin. Whenever we work with any gas law problems, all the temperatures need to be in Kelvin, and the way that we convert Celsius to Kelvin is by adding 273 to the degrees Celsius. So we'll add this in our calculator. We get 319.2. Kelvin, not degrees Kelvin, just Kelvin. So there is our T1 value right here. So now we can plug these into the equation or formula right here. V2 is going to be 86.7 milliliters. Times T1. T1 in this problem is going to be 319.2 K. And we're going to divide this by V1, which is, let's take a look, 577 milliliters. So let's find out what this answer is going to be. We'll take 86.7 times 319.2. And then we're going to divide that by 577, and we'll end up with 47.963. what? Well, milliliters will cancel out, leaving you with Kelvin. So there we go. Our final temperature of this gas, if it's compressed to 86.7 milliliters from this right here, looks like it's going to cool down to 47.963 Kelvin, a pretty cold temperature. Let's take a look at the next problem here. In this problem here, it says a gas occupies this space right here. So this is going to be V1. At this pressure right here, this is going to be P1. And at this temperature right here, this will be T1. What will its new temperature be? We're asked to find T2. If the gas occupies a new volume, which is this right here, which will be V2, and a pressure of this right here, which will be P2. So in this problem here, we have three variables. We're dealing with pressure, volume, and temperature. So this is going to be a combined gas law problem. Combined gas law is P1 V1 over T1 equals P2 V2 over T2. If we cross multiply to get rid of these fractions, what we'll end up with is P1 V1 T2 equaling P2 V2 times T1. And in this problem, we're asked to find T2. We want to know the new temperature of this gas. So if we're solving for T2, I have to divide both sides by P1 and V1. These guys will now cancel. And so the formula that we're going to use to solve this problem will end up being T2 equaling P2 V2 T1 all divided by P1 V1. So there we go. This is our formula that we're going to use to solve this problem. And before we can just start plugging the values in, we have to make sure that the pressure units are the same. So we have atmospheres here and atmospheres here. We're good. We need to make sure the volume units are the same. We have liters here. We have liters here, so we're good. And last but not least, we need to make sure this temperature unit is in Kelvin. It's not. It's in degrees Celsius. So we have to convert T1, which is 5.0 degrees Celsius, to Kelvin. The way I do that is by adding 273, and I get 278 K. So there's T1. So now we can go ahead and plug all these values in. P2 is going to be 8.5 ATM. V2 is going to be, let's take a look at the problem here, 5.8 liters. And T1 is going to be 278K. We're going to divide this all by P1 V1. And what I like to do when I'm working with the combined gas law is I like to put the bottom or the denominator in parentheses. So that way when I enter this all in my calculator at the same time, I can get the right answer. P1 is going to be 5.7 ATM. And V1 is going to be 5.4 liters, it looks like. 5.4 liters. There we go. So I'll go ahead and put the answer down here since I'm running out of room. All right, so we get 8.5 times 5.8 times 278. And we're going to divide that by parentheses 5.7 times 5.4. I'll close those parentheses and hit equals, and I end up with 445.270. So T2 is going to equal 445.270. Let's see what unit we need to attach. We got liters on top, liters on bottom, they'll cancel. ATM on top and bottom, they cancel, leaving us with K. So the new temperature of this gas will end up being this right here. Let's take a look at one more. In this problem here, it says an aerosol can is at a pressure of 7.4 atmospheres and a temperature of 55.9 degrees Celsius. It is then cooled to 7.5 degrees Celsius. The final pressure of the can will be how many atmospheres of pressure. So in this problem here, we've got a gas that's starting off at this pressure right here. So this will be P1 at this temperature right here. That's going to be T1. The gas is changing. It looks like it's cooling to a temperature of this right here. And we want to know what its final pressure will be. Alright, so right off the bat, we know that it's cooling, so the final pressure should be lower than the starting temperature, the starting pressure, sorry. Our final answer should be lower than 7.4 since the gas appears to be cooling off or cooling down. So in this problem, we've got pressure and temperature, and what formula do we know uses pressure and temperature? That is going to be a Gay-Lussac's law, and Gay-Lussac's law states that P1 over T1, it states that P1 over T1 equals P2 over T2. And once again, we'll cross multiply to get rid of the fractions. We got P1 times T2 equals P2 times T1. And in this problem, we're asked to solve for P2. So I'll divide both sides by T1. This will cancel. And the formula that we're going to use to solve this problem is P2 equals P1 T2 divided by T1. So before we can start plugging numbers in again, we need to make sure that the temperature units are in Kelvin. Let's go ahead and convert those. T1 is 55.9. Make this more legible. 55.9. Degrees Celsius. We're going to add 273 to this, and we'll end up with 328.9. We'll do the same with T2. T2 is 7.5 degrees Celsius. And we'll add 273 to this. And we end up with 280.5 Kelvin. Alright, so now that we've converted the temperatures to Kelvin, we can go ahead and plug these into our formula here. So P2 is going to equal P1, which is 7.4 ATMs, times T2, which is 280.5, and we're going to divide this by T1, which is 328.9. So we'll put this in our calculator, 7.4 times 280.5, and we're going to divide that by 328.9, and we'll end up with 6.311. 6.311. I'll put this answer right down here. 6.311. Let's see here. Kelvin cancels out, leaving us with atmospheres. So what is the new pressure of this gas? It looks like this new pressure is going to be 6.311 atmospheres, and since the temperature is decreasing from 328 to about 280 K, then the the pressure should also decrease a little bit, and in fact it does. We started off at 7.4 ATMs and it's decreasing to 6.3 ATM. So here are some review problems or some practice problems using several different gas laws, and I hope you find this helpful.